Hello, class. This is the last, I believe, in the series that we're going to be doing on torsion before we get into flexure, which is the next thing that we're going to be working on. And what I want to look at now is shaft power. And all throughout looking at dynamics and curvilinear motion and everything else, we've talked about omega, right? And omega is not radians, is not revolutions per minute, it's radians per second, right? And that's the engineering use. Technicians use revolutions per minute, and of course the automotive industry uses revolutions per minute. It's easy to see because, you know, when you have a torsion rod, like for a motor or a shaft or a generator or a propeller or an engine, you know, on the end of it, if you were to put a mark on that, let's say that you put a mark on it to begin with right here, and then you start putting it under the torque that you're going to be putting it under. And a lot of you who have ever worked on automobiles understand what I'm talking about with a timing light, where I put that there, and then I start to put it under torque. And what I see is that there's now a rotation of that. Oh God, I used red and yellow. Give me a green, right? So there's now a change, and that, of course, implies that there's been a rotation of the the torsion rod as it's under load, right? As it's under load, and of course, you wouldn't necessarily put it there. You could put it, you know, here, and then see it go to here. You know, mark on the outside, so you can easily figure out what the angle of inclination or angle of twist is going to be. Theta equals TL over JG. And of course, we've already figured out what J is. You know, I should write that here. Theta equals TL over JG, right? And of course, the characteristic of the torsion rod that we've got is going to define what L is. So we know what G is for the material that we're using, steel or aluminum alloy. And then we know what J is for the cross section. Is a solid cross section, hollow cross section, thin wall cross section. We know from the characteristic of the whole problem what L is going to be. And what we can deduce is what T is from finding the angle of inclination, right? So what this gives us is this says that T is going to be theta JG over L, right? So we could figure that out if we know what the design criteria is for that rotation of the thing while it's turning. And that's what I want to really get to. I want to get to shaft power. So when we look at power, how does power compare to torque? Well, we know torque is energy, right? Torque is energy. It's a moment, so it's energy. Power equals energy per unit time. So it would be torque times omega, right? Because radians is dimensionless. So P equals T omega. Now let's see how that works. Because, you know, if we know how fast a torsion rod is turning, and we know the power that this torsion rod is supposed to be putting out, we can also find out what T is, can't we? T is just going to be P divided by omega. I know it looks like a W, but it's an omega. All right, let me have a sip of my tea. So yeah, that angle theta that we have here, right, tells us a lot. We can determine theta not only in a static turn, but we can determine theta even when this is turning a motor, right? When it's a crankshaft on a motor or a drive shaft for a propeller or whatever it is. And that's what I want to point out. But what we have to do, of course, in this instance is we have to turn revolutions per minute into radians per second so that we can use it in the equation. So let's just cut that out. All right, and I want to do two problems that really sort of expand on this and also use our analysis that we've learned in the last couple lectures for torsion shear stress. All right, we're going to look at a hollow. This is actually going to be a bit thicker than the last one that we did. Oh, that's, boy, I couldn't have drawn that worse, could I? But I'm going to tell you what, you know, R in and R outer are. R outer and R in. So I'll tell you what those are, but this is what we're going to be using. And let me cross-hatch it so that you know what is actually the solid material and what is the hole that I've cut in the middle and bored out the middle. All right. So that's what we're going to be looking at. And I'm going to be turning this at 500 RPM. All right. So it's turning at 500 RPM. And we have a design criteria that says that the angle of twist always has to be less than or equal to 1.5 degrees. Right? So that's our maximum angle of twist. We know that the actual length of the shaft, of this hollow shaft, I'll just put length of the hollow shaft, or L sub h, is going to be 3 meters. So it's a little over 9 feet long. We're going to have a design criteria that the maximum, and this is because we've got a safety factor rolled in here and everything else, we've got a maximum stress that we don't want to violate of 60 megapascals. We know that the modulus of rigidity for the material that we're using is going to be 73 gigapascals. All right. And we also know that the radius, the inside radius to the outside radius, the inside radius is going to be 0.4 the outside radius. Okay. Now, what do we want to find in our design? So we're designing this. This is our example, our design example, you might say. So this is our design example, and we want to find out what to fit all of these criterion. Do I have any more criterion? I just want to see. No, we're going to actually find out the horsepower that's transmitted later. That's not really any criterion for this. Although what this is, if you want to, you know, sort of think of what this is in the design that we're making, this would be a hydroelectric generators shaft. This would just be one of them. I mean, you know, we'd have a lot of different shafts hooked up and stuff like this. And so what we want to find out is if I'm using this hollow shaft and I've got this type of ratio, you know, so that's still a very solid shaft, isn't it? I mean, if you think about it, the inside radius is 40% of the outside radius. So this area here is actually much thicker. I should have probably drawn it more like that to show you, you know, how thick it is. And in fact, that even doesn't probably do it justice. So, you know, it's a very thick rod, but they are saving some internal energy, internal material, because this really isn't being used for anything, and it's easier to just hitch on to the outside. And so that's what this is. This is a hydroelectric generator shaft that we're looking at. And we don't want the shaft to turn more than 1.5 degrees. The shaft is about 9 feet, a little around, yeah, 9 feet long altogether, and then 500 RPM is what we're running it at for test purposes. Actually, we probably wouldn't be running this at 500 RPM. We'd be running at 450 RPM, or it'd be running at 900. 900 would be a 4-head, and 450 would be an 8-head synchronous generator used at Niagara Falls or whatever, wherever you've got some large hydroelectric going on. So that's what we're analyzing here, you know, if you really want to know the application that we're looking at. Yeah, I designed this problem from, you know, characteristics of that shaft. So let's get back to this and look at what we've got. Well, if we take the two equations that we have, and I know that I'm going to have torque divided by the polar moment of inertia, right? And that's going to be tau max divided by R outer, right? And then if I also look at the other equation that we have, where have I written these? Yes, there's one equation right there. And the other equation actually I can write right here. Tau max equals TR over J. So, you know, that's basically the equation that I've had here. I've just taken the J and the T, and I've taken the R underneath tau max. So I've used that first equation with T over J. And you know what? I've got another equation with T over J too, don't I? I've got one right here. So T over J, wouldn't that be theta G over L? Does everybody see how I can equate those two things, because both of those are just T over J? You know, let's solve that equation for the outer radius that this thing has to be under our first criteria, right? So if I'm looking at R outer, I would have tau max, that should be times L, now it looks even worse, divided by theta G, right? So I've got 60 megapascals. That's one of my design. And then I also have 3 meters. I have to keep it within that 3 meters. I have to keep this less than 1.5. So what is 1.5 degrees? Well, you know, I could put 1.5, right, degrees. And then what's my conversion factor? Well, if I wanted to find out what 1.5 degrees was in radians, it would be pi radians divided by 180 degrees, right? So the degrees are going to cancel out, and that's going to end up giving me what 1.5 degrees are in radians. I hope everybody sees that and can use that you know, thing well. That's how I look at it. And you know, I'm going to go back in time here. I'm just going to draw, you know, the unit circle for everybody to see, right? This is the cosine X, or the cosine theta, if you want to call it that, sine theta. And, you know, what is this? This is pi radians, isn't it? This is pi over 2 radians. We all know this. This is 3 pi over 2 radians down here. But this is also 270 degrees, right? This is also 180 degrees. So, you know, it's however you want to do it. You can use 3 pi over 2 and 270, whatever. I'm just using this here so that I can use it. And then 73 gigapascals, right? And so this will tell us just with this criterion that I've got right here, and this is the first criterion I'm looking at. Really, I'm looking at two criteria that I'm designing this to when I'm using this equation. I'm looking at this, and I'm looking at this, aren't I? I'm also looking at this. So all of these are included now. You know, you could say, yeah, gee, but this is just an analysis that I'm probably doing of the situation if I use this type of material. And this type of material is dictated, it dictates its own modulus of rigidity. So that's, I don't know if that's really a design criteria. If we do put that all in, though, I get 0.0942 meters, or 9.42 centimeters. Now, if we know that, then we can easily figure out what the inside diameter or the inside radius is going to be, because my inside radius is just going to be 0.4 of my outside radius. You know, actually, I don't even think I had to give you that information, and you could have figured that out yourself, but I'm just going to give it to you, and actually I'm going to figure it out a different way too. So 0.0942, actually, why don't I just do 0.4 times 9.42, and that's 3.76. Yeah, 3.76 centimeters equals R in. All right, no, actually that, I've got all that, that's right, yep, I'm checking everything out. Okay, now, what I want to find out also is what is the maximum torque, right? Because we have to figure out the power that's going through this, if this actually would handle the type of power that we want, right? I'm not going to tell you how this is or what this is rated at, but when we get done, you'll see. So what is the torque then? Well, we know using this equation, where did I put that equation? Oh, using this equation up here, we know that the torque is just going to be my maximum shear stress, or actually I should say my maximum design shear stress. The actual maximum shear stress of this material that we're using inside the generator is far above 60 megapascals. But the design shear stress to keep this way down, you'd never want something like this to fail. Right? Why would you have something like this to fail when all it really, when the only difference is a small amount of material that you might cut out of the inside? This is something you can never get to inside the generator. So you really use a high safety factor here, and the safety factor that they're probably using here is probably on the order of 4 or 5 or maybe even 6 on this torsion shaft. All right, so let's go back to this to find the torque that we're going to use, because we're just going to go back to this this equation right here. And that's just going to be the max shear stress times the polar moment of inertia divided by the outer radius. So max shear stress times polar moment of inertia divided by the outer radius. I have plenty of room to do that. We have 60 megapascals. I was trying to decide if I should use that part of the 6 for parentheses or what. And then this is going to be pi over 2. I'm going to multiply that times r outer squared minus, oh, excuse me, to the 4th minus r inner to the 4th. And then the whole thing divided by r outer. Now we know what those two things are. We know that our outer is 0.0942 meters, and we know that our inner, if we wanted to write it as meters, is just going to be 0.0376 meters. And we're going to want to do that because we're putting it to the fourth. So the last thing we want to do is to use centimeters or something and then try to go centimeters to the fourth, which would be what? What would it be? That'd be 10 to the eighth, wouldn't it? Centimeters to the fourth, I'd have to multiply it by 100 million. That's right, and you'd lose yourself in there. So I always go back to the combination of primary units like megapascals or primary units themselves like you're going to use here. Now, I'm actually going to, let me just check and see if I don't think that I think I'm just going to punch it in. So 60 megapascals times pi divided by 2 divided by 0.0942 times 0.0942 to the fourth minus 0.0376 to the fourth equals, and that is exactly what I had gotten before, 76,781 Newton meters. Wait a second, have we got 60 pascals? Wait, yeah, that should be Newton meters, I believe. Not kilonewton meters, but Newton meters. Let me just check something for a second. Well, there you go. It wasn't a comma. It was a decimal point. So I had 76,781 Newton meters, and in my earlier thing it was 76.8 kilonewton meters. So exactly the same thing. Now, what I want, now that I know what the maximum torque is that I can actually put through there under design conditions, I still want to say we're not designing to failure here. This 60 megapascals probably isn't failure. This angle of 1.5 degrees when the thing is turning at 500 RPM probably does not signal failure at all. These are just the design criteria that you've been given, which include a lot of extra safety in the machine. The machine's going to, work forever. And if it's working at other speeds or under heavier loads, it probably won't break. That's what you want to design for. So we've got this. We know that that is going to be, so what we want to know is how much power. If that thing was turning at its design torque, how much power would it be creating at 500 RPM? How much power would it be creating at 500 RPM? Let's do that. So 76,781 Newton meters, and I could really call those joules, couldn't I? Times 500 RPM. Well, 500 RPM, 500 revolutions per minute. I'm not going to do this every time, by the way, guys. And then one revolution is 2 pi radians, right? And then 1 minute is 60 seconds, right? So we just pop that in there, and this is going to be about 1/10. In fact, I can tell you exactly what it's going to be. It's going to be 52.35. 52.35 what? Radians per second. Isn't that what we got here? Radians per second. And that's what we've got to use. Oh, wait, now that sort of screwed up the whole thing, didn't it? Gonna have to write that again. So P equals T omega since I've already told you put T down there and we know that this is omega, I think I can just give you the answer. And the answer is going to be 4 point, I'll do it this way. Well, let's do it. 4 times 10 to the 6 watts. So it's 4 megawatts, right? It's actually 402, I should put 4.020 times 10 to the 6 watts. I rounded that off. So in case you did the math too, you might have seen that it was slightly off, and I'm just going to put that squiggly line there. That is my disclaimer to tell you that that's, not it. Now, the next thing I want to do is, hey, how much is that power in horsepower? Because we know that there are 745 watts in 1 horsepower, right? So this power right here, if I wanted that power, would also be 5,391 horsepower. And that gives you something that's maybe a little more intuitive. I mean, people know horsepower with cars, with trucks, and that's power, and this is power, isn't it? And that is the relationship between watts and horsepower, which horsepower is still used a lot, especially in the automotive industry. So you should know the conversion between horsepower and just watts. And yeah, so that's the type of hydroelectric power that this thing is going to take and turn into electricity. Excuse me. Yeah, I've done a couple lectures today. This is definitely the last one. I wanted to look at one other problem, though. I may not get through it. May not need that anyway. Yeah, let me just have a sip of tea. Oh, that's better. All right, this is a ship's propeller. And I don't mean a small ship. I mean like a huge Navy ship's propeller. The outer radius is 6 inches. The inner radius is 3 inches. That's right. We're going to do this in the British gravitational system. The revolutions per minute that this thing is turning at, this is just, of course, the feeder thing. For the rest of it is 1,800 RPM. And I'm sure that you can switch that into this. 1,800 RPM is 188.5 radians per second. Yeah, I should have included that anyway. Here's what I'm going to do. I'll just give myself all that extra room that I accidentally cut out of there by come on. I'm just putting my magic white eraser. Nobody can see that. Yeah, everybody can see that. Okay. So those are 188.5. Don't want to write on that because it's still wet, but you know what I mean. So we've got 188.5. I'll write it again now that I've got all this extra room. 188.5 rads per second. It's not rads, actually, it's radians. I shouldn't say rads, because rads actually are another unit of measurement of radioactivity. So we've got that. We also know that the maximum shear stress for this is 10,000 psi. right? 10,000 psi. You know, tau max. Yeah, that safety factor. But for steel, that would be about 200. For a steel, the steel that they're using in here would be around 200. So it's like a safety factor of about 3. Anyway, let's get back to this. So this 10,000 psi is tau max for the steel that we're using in this propeller, the ship's propeller. So we know that the torque, right, on the propeller is going to be the maximum shear stress times J times the outer radius of the propeller. So I have 10,000 psi, right, times J. Now we know that J is this, same pi over 2 times our outer, and our outer is going to be the 6 inches, so 6 inches squared. I'm just going to put a bracket around there. I think that's the best thing. Minus 3 inches squared. Notice I'm using inches because we've got square inches and we've got pounds per square inch, right? So I'm going to get rid of the square pounds per square inch, the square inch in the bottom with the square inches that I'm using here. So pi over 2, 6 inches squared minus 3 inches squared. Wait, did I say squared? God, there it is. I did it again. I'm thinking area to the 4th power. Sorry about that. And then all divided by our outer, which is going to be 6 inches. Now, where am I losing? Yes, so what this is going to be in is inch pounds. So what we're going to get out here when we multiply all of those things together is inch pounds. And I believe that it's going to be, I might do this again, 3.18 times 10 to the 6 inch pounds. Now, I really probably should plug that into the calculator just to make absolutely sure. And you know what I'm going to do first? I'm going to do 6 to the 4th power minus 3 to the 4th power, right? And then multiply that by pi and divide by 2 and multiply by 10,000. And then divide by 6. And hopefully what I'm going to get is 3.18 times 10 to the 6. Fantastic. Yes, that is absolutely right. And then I can believe my next answer too, because if I'm doing inch pounds, right, how do I do it? I'm going to divide this by 12 to get foot pounds, right? Because I'm going to multiply it by 12 inches in the denominator to get rid of those inches in the numerator. So it should be 1/12 of what I've got there. So this is going to be 20. Wait a second. Yeah, 265,000. Yeah, it's just rounded off to that. Foot pounds. All right. So 265,000 foot pounds. That's 1/12 of 3. So it's about, yeah. So that's right. That's both in foot pounds and in inch pounds. Now, what's the power that's going on through that ship's propeller, that supertanker's propeller? How much power is he actually using? Well, it's 1,800 RPM, right? 188.5 radians per second. So let's just do this. T is going to be in, wait, yeah, T is going to be in foot pounds. So I've got 265,000 foot pounds. Right, there's my T, and then omega is 188.5 radians per second. And when I add those two together, I get, I get 49.95, and you're probably thinking that's probably in reality 50. times 10 to the 6 foot-pounds per second. And we all know that there's 550 foot-pounds per second in 1 horsepower, because that's the definition of a horsepower, isn't it? 550 foot-pounds per second. And so if I divide this now by that, that's going to give me 90,882 horsepower for that Navy ship, right? You know, I could also look at this and say that that was 67.66 megawatts of power, because I could use the 745 watts equals 1 horsepower. All right, that's our lecture, and that's going to finish up our lectures on torsion, and we're going to get into the very last topic we're covering now, which is normal stresses in flexure beams, and looking at that. That's going to be about another 4 lectures, I perceive, before we are done with the course. All right, see you at the next lecture.